Welcome back. So let me just start with a review of what we saw last time. I will not be using the full definition of the association schemes, but it's good to review. I think I will be using like in the very beginning, but then we will see a much easier way of proving that something is an association scheme without having to care too much about these things. But nonetheless, let's give a brief review, right? So and let me point out for the Zoom audience, I don't know if Sam is going to be here the whole time, but anything that's on the sideboard is also available here in this website. So in case you cannot see. So what is an association scheme? So it was this pair that had a set X and a bunch of relations on those. And these relations we wanted to think as, there's a vertex set X and it's a color directed graph on top of it, right? Each relation is giving you a color. So there's some technical assumptions. X is non-empty and finite. So this partitions into non-empty subsets is saying exactly this. It's color-directed graph or B-directed graph, if you will. One of the colors needs to be the loops. All the loops need to have the same color. That was the diagonal relation. Every time you give me one color, there is a transpose color, which is just flipping the color. So if there is a red, there's another color called red transpose, which is just red on the other direction. And the most important part was the existence of these intersection numbers, which were related to these pictures here. The idea is that every time you give me, say, a red edge, and you count the number of points that relate to the left-hand side of this red edge by yellow and relate to the right-hand side by blue, this should not depend on the choice of vertices as long as you always pick a red edge. Okay, so this was some sort of version of a strong regular graph, but you put this to the extreme because now you have color graphs, so you have to have all possible strong regularity conditions that you can cook up out of these colors, right? Then we said, okay, but we're not going to be interested in association schemes in general. We're going to use specific ones that have even more properties. Namely, I was always going to be concerned with commutative schemes, which was when these weird intersection numbers, they commuted with respect to R and S, which means that, you swap these two colors, you should get the same number. Another type of scheme was symmetric, which was when the transpose relation was the relation itself. So flipping the edge doesn't change its color. Right.
This is like color undirected.
Yeah, that's the same as saying it's a color undirected graph with loops, and all the loops have the same color, and was the regularity condition. And we also saw that, well, when the underlying set has an abelian group structure, there's a even more specific kind of scheme called translation scheme, in which you require each of the relations to be invariant under the action of the group. This means, you take an edge. If you translate both points by the same Z, it shouldn't change its color, right? Another way of saying this was to say, well, there exists a function such that if I want to determine the color of XY, all I have to do is compute this function at their difference, and it completely determines the color, right? So that was another way of seeing translation schemes. Now, this was the combinatorial view of this object. But we saw that there was a nice algebra associated to it. It was an algebra of matrices. So it's matrices, perhaps I didn't write, but it's Rx cross X matrices. And the idea is that for each relation, you have this matrix AR, which is the indicator of the pair being in the relation. So if you have one matrix for the red color, one matrix for the blue color, and so on. And you take all these matrices and you generate the algebra, right? So you close it under linear combinations and under product of matrices. And then we saw that the condition of commutative was nice because it meant that this algebra was simultaneously diagonalizable, right? Commutative meant exactly that the matrices of this algebra commute, because the product of AR and AS can always be written as a linear combination of the ATs using the intersection numbers. So when you say commutative, it means, these two guys can flip, which means that when you flip these two guys, you get the same thing, right? So saying the algebra is commutative, if the algebra is commutative, you can simultaneously diagonalize. Simultaneously diagonalize, another way you can think is that there is a common bases of eigenvectors, right? So if there's a common basis of eigenvectors, you can bundle them together and say, oh, these are the common eigenspaces, right? So each matrix has its decomposition into eigenspaces, which is a partition of the index set after you change the basis. And then you take the coarsest common partition and allows you to cook up these idempotent orthogonal matrices. Now, if you did not understand the eigenvector stuff, just think that, oh, it's some weird matrices that exist in this algebra such that ER prime times ES prime is always, well, it's 0 if they're different, and if they're equal, it's equal to whatever they are, right? So that's another way of.
These are diagonal matrices.
Well, they're diagonal matrices in another basis. So here I'm not thinking of.
Well, you can diagonal. Since you could diagonalize, you can make them.
Right, but I want to keep the normal basis because I still want to keep the view of the ARs, right? If I change the basis, the ARs also move, right?
Yeah, they become diagonal.
Yes, sure, but yes.
I mean, there's just another way of saying it. It's simply that there's a change of basis
Yes.
of the whole space of the whole matrix. So that, you know, after the change of basis,
Everything is diagonal.
Everything is diagonal, and moreover, these diagonal matrices, each representing one of the original matrices, is just a partial identity.
Yes, you have a partition of the indices, and each of these ARs is you put a bunch of ones in one of the parts and zeros everywhere else. And they're disjoint. Yeah, they're disjoint. Yeah, then when you take the product, if it's different, disappears. If it's the same, it stays the same.
We can, if we change the basis, we can reasonably think of like this partial diagonal as indicating a subset of vertices, right? It doesn't.
Yes, you can and you should.
Sure, yeah.
You can and you should. Not only you can, but you should. So the idea is that somehow, so I did this weird thing where I indexed this guy by R prime, whatever this R prime is, and the way that you want to think is as dual relation. So it is related to this weird partition. In general, it's not very clear, but once you put more properties, it starts becoming more and more clear, because what you can say is that you can come up with the notion of duality, which I'll say when I get to here, right? But in any case, at this point, we have two different bases for the algebra. So this means that you can write each of the bases in terms of the others, and that's the definition of these P and Q functions, right? P is the function that describes AR as a linear combination of the ES, and Q is the function that describes, there's a small typo here, prime S. Q is the matrix that describes the ER prime in terms of the AS, except that there's a normalization factor that needs to be there. If you want motivation for this, think of the Fourier transform. Fourier transform has this, and it is very much related to the Fourier transform.
So these P's and Q's, if you think about them as matrices, they are numbers, but if you think about them.
Yes, it's the matrices that change basis.
Change of basis that you were just talking.
Exactly. With this, we can say, if I give you some other scheme on the same base set, we're going to say that a scheme, this other scheme is a dual of my scheme if the PQ functions of this S prime is the Q and P functions of S, so they're flipped, right? So this is the notion of dual. So when this dual exists, you really want to think of this as a set of dual relations. There's another scheme, and there's a bunch of configurations there, relations there, and these are indexing the relations of the dual scheme. It is not always true that such a dual scheme exists, but for the cases that we care about in this talk, most of them will have dual and will even be self-dual. So it's even better. Okay. So, for example, one thing that will happen a lot is that our schemes will be translation schemes. And this was a fact that I stated last time, I did not prove, but every time I give you a translation scheme, it always has a dual. It's not necessarily self-dual, but it always has a dual. And when, based off of this, if you do computations, that there's an easier way of computing these P and Q functions based off of the dual scheme and the primal scheme, because what you do is you say, well, take any element of your set that has primal relation R. And the way that you're going to compute QS prime of R is you're going to take character Y of X. Remember, X is this guy that has relation R, and you're going to sum over all Y's that have dual relation S prime, right? So that is a formula to compute this Q function.
You didn't define the character.
Character is because it's a translation scheme. So there's an abelian group, so there's a character there. And
so this says that in translation schemes, you just apply the Fourier transform.
That is how you get to this formula. You're going to say if the underlying thing is abelian, you know how to do Fourier transform, so you know what is going to be the basis that will actually analyze. It's the basis of characters. And then when you do the computations, you're going to see that the change of basis is given exactly by this formula. You have to argue a bit because you need to say, well, what is the dual scheme? Because at that point, you don't know that there is a dual scheme, but you can do that. And similarly, you have the dual formula where you flip everything and you say, if I'm given a code word that an element of the set that has dual relation R prime, then I can compute this guy by summing over all Y's that have primal relation S, the character, but there's some weird conjugation that don't worry too much about it. Okay.
I think historically developed in the other direction. I mean, groups existed for ages.
Yes.
From the 19th century, and people understood the power of, looking at the group algebra and diagonalizing it when it's abelian or more generally doing representation. But anyway, in the abelian case, doing this. And then, there are more complex objects like this Hamming scheme and other. And you try to apply the same tools of finding good changes of basis. Of course, it's very powerful in group theory. So you try to do, same, understand it through maybe the dual, through
the difference here is because if you were doing general groups are translation schemes, but you're looking just at the multiplication table. This one, you're sort of bundling up several parts of the multiplication table. So the formula is instead of getting just a single character, you get some sum of characters. That is what's going on here. Okay. So some last definitions. We saw that the valency of R was defined as, the size of R divided by X, which was also this intersection number. And we also defined what was called the multiplicity, which is the dual notion of this guy, which is the rank of the ES matrix. Now, this I did not cover last time, but I will just say a random fact. The P and Q functions are very much related. They have this weird inversion formula where if you take P function of S prime and divide by the valency, you get Q function of S prime of R divided by the multiplicity, except for some conjugation. Yes, multiplicity, which is the rank, yes. So this is the, sometimes we call this the symmetry of the P and Q functions.
Yeah. This isn't only for schemes that have duals, right? This is
this is for all schemes. You can prove this. This is for all schemes. But if you look at these formulas long enough, you can see a very easy proof from translation scheme. But I don't just, you take this formula, you add over all such X. You take this formula, you add over all such X, and you're going to see the two things match. And when you did the addition, you incur the missing multiplication things that are on that formula. But you can prove it for general schemes as well. But it's not like that. Okay, let's see. So we saw some examples of this. So we were mostly interested in the first two examples, which were the Hamming scheme. So we have the weak Hamming scheme over an arbitrary field in which the relations are based off of the Hamming distance, right? So I take two code words, and how do I decide which relation they belong? I just compute the Hamming distance. So if the Hamming distance is 5, it's relation 5.
So it's not code words, it's over all binary vectors, all vectors, right? The Hamming scheme, the X is F.
Oh yeah, when I say code words, I meant over an arbitrary field, but yes, you're absolutely right. So you take F to the N.
Yeah, but it's not a code yet, it's just all.
Yes. So yes, you're absolutely right. So you take strings of length N over a field and take two such strings and you determine the relation based off of their Hamming distance. And I claim that the P and Q, well, this was a very nice scheme. It was a symmetric translation, self-dual. And I claim that this is the P function. It's called the Krochek polynomial. It's this weird alternating sum of products of binomials. Okay.
It's very easy to calculate if you put your mind to it.
Yes, if you use this formula, it's not too hard to compute. It's not too hard to get to this. It's a combinatorial problem. A strong version of that, as the name suggests, is the strong Hemming scheme, in which not only do you keep track of the Hemming distance, but actually you keep track of, I give you X and I give you Y, you take their subtraction, call that Z, and you count how many things in Z, how many positions have 0 in Z, how many positions have 1 in Z, how many positions have 2, and so on. Right? So you keep track of all these counts, and that is the strong Hemming scheme. And then you lose symmetric, of course, if the field doesn't have characteristic 2. So you only get commutative. It's still translation because it depends only on X minus Y. And I said that it was self-dual and has this more complicated formula for the P and Q functions. And again, actually, it's just a combinatorial exercise, but it gives you a more complicated formula. And finally, the last example that I mentioned was the Johnson scheme, which is morally, you take the Hemming scheme and you restrict it to a layer. So another way of seeing this is the base set is just the subsets of n of size exactly W, and the relation sets is you just look at the size of their symmetric difference, right? And this was the Johnson scheme. It's very easy to see it's symmetric. It's not so easy to see that it has no dual. The way that you see that it has no dual, you have to do all the computations, get the P functions, Q functions, and you check what would be the intersection numbers of the dual, and you find out that they would be fractional. And then like, okay, so there is no dual. Okay, but we don't bother too much about this example. It's just an example to have in mind that, association schemes don't need to be that well behaved. Okay, so any questions so far? Okay, so why were we interested in this? Well, the reason was because we were mostly interested in these codes. So a code over any scheme, not necessarily Hemming scheme, was just a subset of the underlying space that was non-empty. And the idea is that we wanted to use the scheme to inspect the code, right? So the scheme can see a couple of things about the code. Namely, it can see what is called the inner distribution of the code, which is this function here, AC of R. What you're going to do is you're going to count the number of pairs of code words in this code that relate as R, and then you normalize by something, right? So I give you, say, a code of the Hemming scheme, and then you say, well, how many pairs of code words exist in this code that have distance 1? How many pairs have distance 2, right? And you just keep track of these counts. Now, when your translation scheme, when your scheme was a translation scheme and your code was what's called an additive code, which is a subgroup of X, then there's an easier way of computing this, which is you just count how many code words, not pairs of code words, just how many code words have the FS function giving something, right? So in the Hemming scheme, this is much more easy. You can just say, I give you a linear code in F to the N. You just count how many code words have Hemming weight equal to 5, and that will give you A5 or AR5, whatever, right? So that's a much easier way of computing in the case of additive codes or linear codes, if you want, in a translation scheme. Now, we were mostly interested in what were called V codes, in which we say, well, this AR is not allowed to take all possible, I cannot see all the relations. I want to restrict some of the relations to not appear at all, because at the end of the day, we want to think of things like, I have the Hemming scheme, and I have a code in which the distance of the code is at least, say, 10. What does that mean? It means that on relations 1, 2, 3, up to 9, I cannot see code words. So I cannot see a pair of code words.
AR is 0.
Yeah, which means AR on those guys is 0, right? Another way of writing this is the support of this function is contained in a specific set V, right? I specify and say the allowed distances will be 0 or anything larger than 10, right? And so the support of this function needs to be contained in that. And the point was that you can now use properties of these schemes, namely you can use what were called McWilliams inequalities, which is this line here, to cook up a linear program that would give you an upper bound. Because what is this linear program doing? Well, you maximize this. This sum of the ARs, if you do this for this guy, you're just going to get size of the code. It's a simple computation. If you do this computation for AC, you're just going to get size of the code. We saw last time that anytime I give you a code, this kind of inequality is always true. So this weird combination using the Q functions is always greater or equal than 0 for every fixed dual relation. So these were the McWilliams inequalities. So if I plug AC, it will always satisfy this. It's also easy to see that A of the diagonal is 1 because it amounts to code cross code XX for X in the code divided by code, which is just 1. This is AR equals to 0 whenever R is in R minus D is just this condition that the support is contained in D. And of course, these are counting things, so they're non-negative numbers. So this linear program is a relaxation, right? So if you're thinking of codes, you also know some sort of version of integrality of these ARs, right? They cannot be any real number. They need to be sort of almost integers, except that there's a weird normalization here. Maybe in the linear case, it's very easy to see that they're actually integers. So you have some weird integral program, and this is a relaxation of it, right? And if this is a relaxation, it means that the size of the code is always upper bounded by the optimal value of this relaxation, right? Now, yes?
Could you please remind why the McWilliams inequalities are the right things to put here? I mean, that they're strict enough or complete in some sense?
Oh, so they are not complete at all. So we know that at least if you pick N and D carefully, you run this program, you get some optimal value, and it's not the actual size of the true code.
Regardless of integrality stuff, just the McWilliams inequalities by themselves.
It's just you put in every relaxation you ever do, you put everything you know in.
Right.
All the inequalities. This is everything that's general. That's no.
Yes.
This is everything we know.
Yeah. These are the only.
Yeah. At this point, it is everything that we know, but it's not enough to give you the precise value. So, you can put more things, and we will put more things, but to put more things, we'll have to do some tricks. But that's sort of the point. We want to close this gap. We know that the gap exists. We do not know if the gap exists asymptotically, because we're mostly interested when N is going to infinity. And maybe, okay, there is a gap, but the gap is going to 0 as N goes to infinity, or at least not necessarily going to 0, but you care about exponential scale. So maybe the gap is sub-exponential and then you don't care. This we do not know if this happens or not, but we know that the gap does exist. This we know. Maybe the gap gets smaller, but it does exist. So we want to close this gap somehow. And we will show that you can actually close this gap by doing something somewhat, in retrospect, you can see it a little bit as silly, but at least is a good proof of concept that you're in the right track. Okay, any other questions?
I don't think in retrospect you can see it as silly.
Okay.
I cannot even imagine how anyone will see it as silly.
Okay, sure. I mean, when I'm done, we can return to this remark and we'll discuss. Okay. So, but then I think the last thing that we saw last time was that you could just say, well, this whole thing is way too complicated, and I know a little bit of graph theory, so you might as well use direct optimization techniques from graph theory. Namely, I can just say, let's define this graph GSD, where the vertex set is just the same set as the underlying set, and I put an edge every time I see a pair that is not in D, right? D is my set of relations that are allowed, right? So if I consider this graph, then a D code, written this, a D code is just an independent set in GSD, right? It's very easy to see because, it's just a set here that doesn't have any edge inside it, right? Because edges correspond to things that are not in D. So you could use standard techniques from graph theory or optimization over graph theory to say, yeah, I can use what are called the lowest theta function or even the lowest theta prime function, which I did not write the program here because it's not relevant. But the point is that you could use that instead because maybe you're just interested in the symbolic analysis. So a priori be even a better bound because that uses power of semi-definite programming and not just linear programming, then you might think that it is better, but Shriver said actually it's not better. It's exactly the same. The optimal value of the Delsarte LP is exactly the theta prime over there. So it's not very important now what the theta prime is, but the Delsarte LP is sort of factoring out the redundancy on the theta prime. That was sort of the punchline of the last part of the last talk. Okay, right. So any questions about all this? And I think that would finish the review. Any questions? This means okay, or means I have a question. Okay. So now we're going to see one other type of scheme, which are Shurian schemes. So Shurian schemes will actually take into this perspective that Shriver said that, you know, this Delsarte LP, somehow you're just factoring the redundancy. In Shurian schemes, what this redundancy is actually going to mean is actually symmetries that happen on the space, right? So if you think of the Hemming scheme, there's lots of symmetries, right? So what is a Shurian scheme? We're going to do the following. So imagine that I have a group G, and here G does not need to be abelian at all. It's just a general group. Doesn't even need to be finite a priori. Normally it will be finite. And let's assume that G acts on X transitively. Okay. Now, every time I have an action of G in X, I have an induced diagonal action.
Everybody's okay with this?
Yeah.
Action transitive, yeah.
Okay, good. You have the induced diagonal action. Of G in X cross X, right? So this just means, you know, take a sigma here and act on both of the coordinates at the same time, right? And what we're going to define is what is called, so maybe let's call this action theta. S theta is this pair here. So what do I mean by this? This is just the orbits of the diagonal action. Right? And this is what is called the Shurian scheme. Shurian scheme corresponding to this action, of course. Now, this is always a scheme. So let us check that this is always a scheme.
But do you want to, before that, do an example, like if we look.
Oh, I'll give you.
F to the n, actually.
Yeah, so the spoiler is these three guys are Shurian schemes in disguise, but it will take a little bit of work. So let me not do that. Let me just do this proof because this proof is very easy. Okay. Okay, so let's just check this. So X is finite. Okay, maybe I should have assumed that X is assumed to already satisfy 1 because it has nothing to do with the action. So X is non-empty and finite. R partitions X cross X. This is completely obvious because these are orbits, right? The diagonal is one of the relations. This is where this comes in. If the action is transitive, then the diagonal will be one of the orbits, right? Because once I take XX, the action is transitive. I can take it to any X prime, right? So this is also obvious. R and R transpose, this is also obvious, right? So if one of the orbits looks like something, if you transpose, it's another orbit, right? This is also obvious. The only thing that is perhaps not completely immediate is this guy, but it's not that hard because, you know, what does it mean that X, say G dot XY this is the orbit of XY. What does it mean this? X prime, Y prime. Well, this is the same as saying that there exists some sigma in G such that, you know, sigma dot X, sigma dot Y is equal to X prime, Y prime. right? So that's what it means for them to be in the same orbit. So let's try to compute what would be the intersection number based off of xy. Well, these are the z's such that it relates to x as r, and it relates to y as s, right? And imagine that x, y has some relation t. Well, by just doing a change of variables, you can just write, u in x, such that this is x sigma minus 1 dot u in r, and sigma minus 1 dot u y in s. Right, so this is just a change of variables, and sigma is this sigma, right? And then, well, this is an orbit, this is an orbit. So if I act with sigma on both of the coordinates, I don't change whether it's in R or in S. And when I do that, magic happens because I get sigma dot x, u in R, and u sigma dot y in S, right? So, and then I'm done because this is y prime and this is x prime, right? So when I try to compute the P RST based off of x and y, I get the same count as if I did for x prime, y prime, right? And that is this thing. So I did not claim that this is commutative symmetric translation. These I do not necessarily true. Shurian schemes are schemes, not necessarily commutative, not necessarily any of these three might not hold. Okay.
Even if G is a billion, it might still not be a translation.
It might still, okay, a billion, it will be commutative because, oh wait, it depends on how you act, I guess. No, even if it's a billion, you can fail. Even if it's a billion, you can fail, I think. Depends on what the action is. Because you could have something as bad as, well, I guess the trivial action will give you commutative, but okay. Some examples. So I claim that all these guys are actually Shurian schemes. So how do we see that? Well, let's start with the easiest one. The easiest one is this guy. What is the action that gives you this scheme? Well, there's a very natural, what?
Computation.
Yes, exactly. There's a very natural action of Sn on the set, right? Let's call this theta in W. And what is the action is, sigma dot A is just the image.
Use the names of the elements in it.
Right. And it's not hard to see that the two guys are in the same orbit of this guy, if and only if they're in the same relation. Okay, or on the diagonal action. Okay, on the diagonal action, take two sets and you permute both of them with the same permutation. Where do you land? You cannot change the size of their intersection, right? Or the size of their symmetric difference for that. That's intended purposes. So this is a Shurian scheme exactly for this action. Okay, so that is the easiest one. Let's go to the second easiest one, which is this. Well, this now this is a little bit more complicated. So the first natural action that you can see here is the action of Fn on itself by translation, right? And these actions are, I should say, this is obviously transitive, which I forgot to say, which is required by the definition, but it's obviously transitive. Translation. Right, so this acts on itself by translation, and it's not the correct action. If you factor this out, you're going to see that you don't get the Hammett scheme. Now, there's another action on this set, which is essentially that action going on. And here is more convenient to write it as a right action. And here, this action is x dot sigma, if you want the position I, is just x sigma I. And so here, x is Fn, sigma is Sn, and I is a position.
It's the same action as before.
It's the same action as before.
Just permute the names of the elements.
Exactly. You're just changing the labels of the bits, right? Or the over an arbitrary field, right? Now, so you have these two natural actions. Neither of them gives you the correct scheme, but the point is that them together gives you the correct scheme. There's a little bit of annoyances because these actions don't commute with each other. So if you want to put them together, you need to do a little bit of algebra, which I will skip. but you have to put them together into some semi-direct product, which I technically should specify what this is, but I will not. But putting just think that both of them are acting on at the same time. And when you put these two together, you get some action, theta n f star. And the corresponding scheme will be exactly the strong Hemming scheme. Now, I will argue why this is the strong Hemming scheme. So the way that you can argue is slowly. So first, let's not do the diagonal action yet. Let's just look at the normal action of Sn over Fn. When are two code words in the same, or 2 points of this in the same orbit of this? It's exactly when they have the same counts of all the letters, right? Because you're just changing the names of the positions, right? So the orbits of this is precisely just looking at the counts. Now, on this action, when you look at the diagonal action of the translation, when are the 2 pairs of strings of Fn in the same orbit? It's exactly when their difference is the same, right? So sigma dot xy is equal to sigma prime dot xy. Perhaps I should write this translation. So x plus z, y plus z is one of the actions, right? So this is the orbit of x, right? Of xy, right? Xy can be mapped to these guys. Which means that what are the guys that have this kind of form is exactly the guys where you know their difference, right? So this factors down to the difference, and once you're factoring down to the difference, this action comes and says, well, I only care about the count, right? And then that's how you get the strong Hemming scheme, right? So just an informal description of this. Okay, and finally, how do you go from this to the weak Hemming scheme? Well, to the weak Hemming scheme, you have yet another action going on. You can take the multiplicative group of the field, take n copies of it, and this acts on Fn by pointwise multiplication. And now, what does this action do? This action essentially erases the information about non-zero things, right? As long as 2 things, as long as I take something here, and if I act with this with the orbit, everything that's non-zero can be mapped into everything that is non-zero, and things that are 0 can only be mapped into things that are 0. So when I compose all these 3 actions into a complicated semi-direct product, which needs to be done in the correct order as well, then you're going to get that the corresponding action gives you exactly the weak Hemming scheme.
Is there any association scheme on which there is no non-trivial group action?
You can cook them by hand.
So you can always cook, right? Because it's so homogeneous that there must be at least.
Oh, no. I'm saying you can always cook a scheme that does not have an action by hand.
Really?
Yes. And it turns out
like the regularity or homogeneity of this.
Yeah, I don't think it follows, because the condition of Shurian essentially amounts to saying that the Bose-Meissner algebra corresponds to the algebra of invariant matrices, and this is not always true. Essentially boils down to that, but it's I don't know of any natural examples, unfortunately, but you can cook them by hand, and even cooking them by hand is not that easy, because at least the one that I know relies on, you need to first find 2 coherent configurations that are not isomorphic but have the same numbers, which is not easy already. So
non-isomorphic respect.
Yeah.
Just to make sure I understood this conversation, so basically all the natural cases are Shurian schemes.
Yes, all the natural cases and all the cases that will appear in the talk from now on will be Shurian. And in fact, this is my shortcut, because I will present another scheme, and to show that it's a scheme, I'm just going to say it's Shurian. Here's the action. Okay. Right. So any more questions on this? Okay. Okay. So now let's go back to our favorite scheme, which is the Hamming scheme. And remember that the Delsarte LP, at least I told you, does not actually find the correct value of codes. And we even saw a little bit better, right? Even if you're dealing with linear codes, we said, well, linear codes, you know that the Mac-Williams inequalities behave a little bit better. They have some integrality condition, but it's very hard to explore directly this integrality condition. So now we want to somehow explore better this condition, but to do so, we need to go to a different scheme. So we want a scheme that captures more information about our codes, but we also want to keep the fact that it is a scheme, right? Because if we just keep track of everything of our code, the annoyance is that maybe we'll land on something that looks like theta prime, which is a semi-definite program. Okay, maybe you can go to higher. If you know theta prime is part of the SOS hierarchy and you can go on higher levels, but that is annoying because it's semi-definite programming. We want to keep the fact that it's a linear program, and we want to keep the fact that it looks very much like it's the Delsarte LP of some Hamming scheme. That's what, of some scheme, that's what we want to keep. So the idea is that we're going to keep track of more information. So in the Hamming scheme, or at least if you think in terms of the linear codes, we were keeping track of Hamming weights of single code words. So let's try to now keep track of Hamming weights of more code words. So here's what we're going to do. We're going to say that the symmetric difference configuration and I'm putting symmetric difference in parentheses because I'll just be calling these configurations, but there will be another kind of configuration as well of. Now, instead of picking just a single guy of f to the n, and maybe let me just do the binary case, because the non-binary case is more complicated, so I'll skip it. Instead of just picking one guy, I'm going to pick an L tuple of guys. And I'm going to insist that there's an L tuple of code words rather than a big code word of length NL. I want to insist that there's an L tuple of code words of length n, because this is going to be a function config x, which goes from subsets of L to 0 up to n. And the way that this function is defined, so every time I give you an x, it's a function. And the way that this function is defined is if I want to compute this at j, this is going to be, you take all the indices in j, you sum the corresponding code words. Remember, this is an L tuple of code words. So I don't know, if j is 135, take the first code word, the third code word, and the fifth code word, sum them together, and compute the Hamming weight. So this is Hamming weight.
Sub j is a string of n.
Yes, yes.
Yeah, it's exclusive of
yes. So
j vector.
The reason why it's called symmetric difference configuration is because the other way you can see this is it's the symmetric difference of the supports of the code. Right? So if you think of code words as just sets, you're just taking the symmetric difference of specific code words, right? If j is 135, it's the first set, the third set, and the fifth set. Then you take their symmetric difference and compute their size. Right? Now, it will be convenient to also say something about.
If L is 1, then you get the Hamming weight of x, and you also get 0, which is uninteresting.
If L is 1, yes.
L is 1.
Yeah. If L is 1, you can see that you're just capturing just the Hamming weight because, okay, it's a function that has 2 possible coordinates. On the singleton is the Hamming weight of the code word. On the empty set, it's always 0. And the empty set is always 0, so it's sort of, the empty set doesn't carry any information here. But yes, this is a generalization because you're keeping track of a little bit more information, right? So another type of thing that you could keep track of is try to keep track of more information, quote unquote, is obviously not going to be more information, which is the Venn diagram configuration. And when it's Venn diagram configuration, I will always say Venn diagram to not confuse. So configuration means symmetric difference. Here, I will always say Venn diagram. So of x, it's going to be config. So it's a function that looks the same, but I'm always going to put the v to distinguish for Venn diagram. And config x of j is you're going to look at the size of the corresponding Venn diagram cell. So it's this. So the way that you want to think of this is, I think I can get rid of this. Let me draw an example. In the case L equals 2, right? In the case L equals 2, imagine that you have two code words and they correspond to sets, right? And here are these two sets. So this is x1 or support of x1. Support of x2. And for example, if you want to do config x of 1, 2, for example. So this is the symmetric difference configuration. This would be this set, right? This is the symmetric difference configuration. Right? But if you wanted to do, for example, config orange, config v x, say 1, 2, then you need to compute the intersection because it's the guys that is the points that belong to both the first code word and the second code word. And if you wanted to do, I don't know, yellow will not be visible. Try green. Config v of 1. This is the points that are in 1, but not in 2. So this would be, this set. Not intersection and not there. Okay. So it's different than the usual configuration of 1, because the usual configuration of 1 would be the first code word. Okay. So you're keeping track instead of, you have 4 cells in the Venn diagram and you're keeping track of those information. But of course, if you know your inclusion exclusion, you know that this is the same information, right? Because there's a very easy formula. Well, okay, maybe not easy to, if I put you under pressure, it's not easy to say, oh, it's this formula I know by heart, but there's a very easy conversion. One of the sides is actually easy. So for example, if I write if config x is equal to some function g and config vx is equal to, let me write gv, then how do you compute the symmetric difference from the Venn diagram? This is easy because you just say sum over all cells such that the intersection is odd, g v k. That's the easy formula. The hard formula, which I will not prove, it's just inclusion exclusion, is if you want to the gv based off of this, you're going to do something like indicator that j is empty times the size of the space, which is n, plus 2 to the 1 minus L sum k L minus 1 to the j enter k minus 1 g k. That's the formula that goes back. Okay.
This is just inclusion.
It's just inclusion exclusion or Mobius inversion if you want to do more fancy stuff.
Is your hierarchy level, right? It's going to go up to.
Yes, it's going to go up. So for each L, there is such a heavy. There's going to be a scheme corresponding to that in just a second. So L, I want to make L go larger and larger because then I can keep track of more and more information.
Larger and larger isn't like a big constant. It's n or something. Right?
Well, for the completeness, it will be n. But a priori, you could just say, well, let me try to run the hierarchy at level 5, right? And a priori, it's better than running it at level 1, right? Because at level 1, you're just keeping track of the original Hamming scheme. Well, I didn't write yet the definition. So everyone is fine with these definitions of configurations and symmetric difference and Venn diagram configuration. Okay, good. So I think now I'm ready to actually introduce the actual scheme, which I think is just behind here. So what we're going to do, I guess unfortunately the configurations went away, but this is the order L Hamming scheme. So every time I give you some level L, we're going to do a scheme whose base set is L tuples of code words. I guess here I'm actually defining only the binary one. So yeah, so I should say this can be done over general fields, but the formulas become more complicated, so I'm going to skip that. This is the binary order L Hamming scheme. And what do I keep track of what's the information that I keep track of is exactly these configurations. So the relations, I'll have one relation for each possible function that could be configuration. And the relation is exactly, you take the pairs of L tuples of code words, and whenever their difference has a certain configuration, you put in this relation, right? So for each G, each of these is an L tuple, so you take first code word of X minus first code word of Y, that's going to be the first code word, and so on, right? So you take code word by code word, you take their difference, now you have an L tuple in your hands, compute the configuration. If it's equal to G, it's in this relation. If it's not equal to G, it's not in this relation, okay? Now, for the binary case, it's easy to see that it's symmetric because, you know, I'm just taking subtraction, and of course, assuming that you're putting the natural abelian group structure that is there, you get something like, I said symmetric, but what I meant was translation, which it's also true that symmetric because minus doesn't mean anything on binary. I will not prove that it's self-dual. This is the weird higher order Crotchet polynomial is this weird formula is very much similar to what happened on the strong Hamming scheme for essentially because when you do the computation with the characters, you land on a very similar combinatorial problem. But I will prove that this is actually a scheme by showing that it's Shurian, right? I will show what is the action. So the action is the following, right? So the first is the natural one that you would expect. Because it's translation, you're most likely going to include the natural action of this in itself by translation. But again, just as in the Hamming scheme, this is not enough to get you the scheme. This is going to give you way more relations than you would like. So you need to
the symmetric group on L to compute.
So no. So if you do a symmetric group, so what do you try to do the Reef product or something like this?
Well, I mean it will matter for the configuration.
Yes.
So yeah, you cannot change the order of the vectors in this.
Yes, a priori you cannot change. So if you remember, we had the natural action by permutation of Sn in Fn. This gives you a diagonal action of Sn in this F to the N to the L. Meaning that when you permute all of the code words at the same time with the same permutation, okay? So each of these guys is an n-bit string and you use the same n permutation in all of them, right? Now, when you put these two together, you're gonna get these weird semi-direct products. Again, they don't commute. And you get this weird action of the semi-direct product, and the claim is that this happens. I guess I'm only doing for F2, so let's not. The scheme of this semi-direct product action is actually this scheme. So let's see why. So again, the translation is responsible.
To say what you're acting on. You're acting on the Hamming scheme.
I'm acting on F2 to the N to the L, right?
But I mean, okay.
Right.
Yeah, you get the Shurian scheme by acting on a space.
Yes, yes. It needs to be a transitive action, but just the translations already gives you the transitive, right?
You need to act on the diagonal, right?
Right. So this action induces a diagonal action, and then it's the orbits of the diagonal action.
Like in the weak Hamming scheme, you need to clear out the information on non-zero entries. You don't seem to be.
Oh, because I'm doing binary.
Okay, yeah.
If you do binary, it doesn't matter, but you're absolutely right. This you would get like the strong version of the hierarchy if you just do that. If you want the weak version, you also have to do the multiplicative group. You're absolutely right. But I'm skipping that because defining configurations is more complicated, etc. Now, and the way that you see that this is actually the correct scheme is similar to what happened on the strong Hamming scheme, or even the weak one if it was binary. It's not too hard to see that if you just consider the usual diagonal action, just this action, then if x dot, so x, maybe I'll write it like this to be explicit. I give you some L tuple of code words. This guy, the orbit under just Sn, is the same orbit as y1, yl, if and only if their configuration is the same. So here, it's not the diagonal action, it's just the normal action at this point. Of course, because we know configurations keep track of the same thing as the Venn diagram configuration, the last equivalence is obvious. And if you think in terms of Venn diagram configuration, it should be clear that Venn diagram configuration keeps exactly track of the orbit, because once you know I guess it's hidden. Once you know how many points of the space are in each of the Venn diagram cells, changing the names of the points doesn't change this, right? And it's if and only if, right? So if I know how to permute to get to the other, their Venn diagram configuration needs to be the same, right? So the equivalence of this with this is sort of obvious, and the equivalence of these two is just that there is some formula to translate one to the other.
Why did you say this is not the diagonal action?
Oh, this is not the diagonal action.
Sn permutes as the coordinates.
Oh, sure. It's right. It's the diagonal action here, but it's not the diagonal action that defines this thing, because you need to do it on x.
Yeah.
Yes, you're absolutely right. This is also a diagonal action, but technically you need to take the diagonal of the diagonal. Okay, and then it's the same thing, right? Because this action on pairs of tuples amounts to saying I'm only going to care about x minus y, and once you act there, the diagonal version of this on pairs of tuples, along with this, we're going to say x minus y. I only care about the configuration of x minus y, which is exactly the definition of the relations. Okay, so that is the proof that this is actually a scheme, right? And the other properties here are obvious. Symmetric and translation is obvious. Self-dual is not obvious. So okay. Okay.
Well, what about the SL action? Don't you also want an SL action?
What? Can you repeat the question?
Yeah, so you could also have an SL action.
Yes, I will get there in just a second. Not actually even SL. I'm going to put even better than SL. But it will come soon. It will come soon. But defining this is very convenient if you're thinking about actually running the hierarchy. Once you put the SL action, well, SL is still fine, but once you put the other action that I will put, it will be less easy to actually run this on the computer. So this is good for purposes of computation. For purposes of showing the completeness, we'll actually care about another action that is hard for computation, but is easy for symbolic analysis. Okay.
You should consider a break sometime.
Yes, I think I was going to exactly see if I want to break here. Let me just do one more thing and then I'll break, which is, let's connect this to the original Hamming scheme, right? Well, how am I going to use this guy? Because now the space changed. I'm actually interested in the original Hamming scheme. Now, granted, you could say, aha, this is I could use, length NL here. That's not what I want to do, right? I do not want to think of this as, the space of things of length NL. I really want to think as L tuples of N things. And what I'm going to do is I'm going to say, unfortunately, I have to hide this. Yes, the advantage is that the configuration is back. So imagine that I give you a decode C, but over the usual Hamming scheme, right? So this is the guy that I'm interested in, right? So, and I'm going to even do binary, right? I'm interested in these guys, right? It's a D code over the usual Hamming scheme. Well, whenever I have such a thing, I know that if I take C to the L, right, just C Cartesian C L times, this is going to be a DL code over this fancier scheme. And what is my DL? Is just the set of things indexed by configurations. And what I want is that anytime I give you any element of L, G of the singleton J is in D. Right? Why is this a DL code? Well, it's because when I take configuration of X minus Y, and let's assume that both of these guys are in C to the L, if I evaluate this as J, then this is just going to be the Hamming weight of Xj minus Yj, which must be in L, in D, right? Because these are two code words, and this is exactly their Hamming distance, right? So that's the proof that this is a DL code. Therefore, I could use this guy to upper bound codes over the original Hamming scheme, right? Because if this guy is a DL code, I know that C to the L is at most the optimum value of the Delsarte linear program of this weird scheme. Of DL, right? So it's at most this, which means that I can just say, okay, let's pass this to the other side. And I might as well give myself a lot of room and use all possible choices of them, right? So that's one way that you could use this to analyze codes over the original Hamming scheme. Turns out, well, I will not prove this, but this is actually not a very good idea. For general codes, this doesn't give you anything useful. We can actually prove that if you just do this, all these guys actually give you, the right-hand side is always the same. Infimum doesn't gain you anything, but I'll not show this. We'll be mostly focused about linear codes. And for linear codes, you can do something slightly smarter, which is just a small subtlety, but it makes the whole difference, which is if C is linear, then C to the L is also linear, and it's a DL lin code. So you can do something slightly better, which is to use this DL lin, which is just the RGs, such that the image of G is contained in D, right? Because if you do config, so now because it's,
What do you mean by image?
oh, it's a function. G is a function. It's a configuration. Right. So remember, now that I have a linear code, it's obvious that C to the L is linear. If I want to know the inner distribution of that, the ACs, is enough to just compute, well, I guess I can just do it like this. Let's do this with X minus Y, but let's compute in an arbitrary set J, not just a singleton J as we did here. Well, this is just going to be the Hamming weight of the sum of J's in J of Xj minus Yj. Maybe with parentheses, doesn't matter. But now the code is linear. So when I take any linear combination, it's still a code word in the code. So this still needs to be in D because the code is linear, right? So you can put extra restrictions. That's the point. And you have the same sort of bound, right? So C linear, right? C linear shows that if of right? And in the second part, what we're going to see is that when L is greater or equal than N, this is tight. Well, what I mean is that, the optimum value max of C, such that C is linear D code, is exactly equal to the LF root of ODT LHN. I'll even write for F because it's true for F, even though I didn't actually write it. There's a version of the old-in, of course, over there. That's what we'll see on the second part of the talk, but I'll break here. Okay. Okay. So now, oh yeah, I should say, right, so this is joint work with Fernando here. So it's a joint, both the definition of the hierarchy and this as well, with Jeronimo. And Chris Jones. Okay. We want to prove that completeness thing, right? And if you look back at the Delsarte LP, it's very hard to figure out, right? So I guess I still have the. So you have these weird projects which have, there's some weird product of multinomials, even worse. It's alternating, so there's some minus ones.
Wait, can I just stop you for
Yes.
one question? Does it make any sense to look at L larger than N? Is this
Oh, you can.
just redundant?
A priori,
A priori you can, right? But let's also do a sanity check, right? L equals N is really a natural place to look
That's
at, right?
because
Because
you should have all the information already, right?
yes, but at least for linear codes, it's very natural, right? Because once you take L code words, this kind of configuration is able to look at Hamming weights of anything in the span of these code words. And if you're taking L at least n or exactly n, you already see the whole space, right? Because you see things of dimension n. But notice that if you go for nonlinear codes, n is not necessarily that natural. You might think that, okay, maybe I need to see a little bit more because I don't have linearity. And you could go to, say, 2 to the n, say in the binary case. And what is surprising is that I told you that this doesn't actually work. For any L, this doesn't move. It's always the same value. But here it moves. So it's kind of weird because something is going on.
The theorem is just for linear.
The theorem is just for me. We also have a theorem that says this doesn't move. For this one, it doesn't move. It's not that we don't know if it moves. We know it doesn't. So
I don't know if you tell or well, N is very natural. The first theorem they used to have is N squared.
oh yes,
It's not, it's natural, it's not obvious that you can prove that this is about.
So this is surprising to me. Like why?
no. I mean the reason why we had n squared is because we could only prove n squared. That point, and it's not even completeness, but this is the natural place where you would expect completeness. Maybe even less than n. Maybe if you would know what was the dimension of the optimal code, maybe by that dimension plus 1, you would expect to already see it. We think this is not true, but by n it is true. But we're going to do it so like more general, say if it's above n is also okay, right? So you're not losing by overshooting if you wanted to overshoot. Now let me also point out that you would never actually run this by this level, because if you're running by level n, you're essentially already doing brute force. Just to state the program,
Yes.
you already have to brute force over the whole space, so you would never actually run. So this is mostly a theoretical thing that is saying, yeah, this hierarchy is gradually improving, and if you did it on a stupidly large level.
Of convergence?
No, we're not going to say anything about rate of convergence. Yeah.
Something that's not known also for all the usual hierarchies.
Yeah, so SOS, you have something similar. If you're doing SOS for independent set, you know that by something like 2 times size of the independent set plus 1 or something like that, the hierarchy actually sees the value, but by that point, you're essentially doing brute force anyway. So it's okay. And people, I mean, for arbitrary graphs, we don't know how fast it converges. We have some results of like for a random graph, we know that it's actually pretty bad, the convergence, very low levels don't see much. But I'm not going to be focusing on that, even though because we do not even know about these. Okay, any more questions? Right, so we aim to prove this sort of completeness, but if you look at these Krawchuk, these higher order Krawchuks, and you look at the Delsarte LP, it's not clear at all how this thing is actually going to be able to see the size of the true code, right? Because these guys are somehow conspiring together to push the value down, right? So this is a maximization problem. So it's going to overshoot the true size. And somehow these weird alternating things, the alternating functions are conspiring together to push this down, right? So the way that we're going to do it is we're going to actually move to a different scheme and argue that the Delsarte LP matches the value of this Delsarte LP. So we're going to go to an even other scheme. So let's see. So this is what I'm going to call the order L subspace scheme. And here, from now on, I will be assuming that L is always greater or equal than N. Always L is greater than N. You can define these things for L less than N, but some technicalities start popping up, and I'm not going to bother too much about this. But I will be doing over non-binary ones because I think all the technicalities all the things that make it complicated for general fields already go away by this stage. So what is this? So I'll write this as S for subspace in FL. Yes. So the base space is going to be the same as F to the N to the L. And now the relations are going to be different. Are NFL. And the idea is that I'm going to index this.
Look at the span of the elements.
Yes, so I'm going to index this by subspaces. So L, and here L is Fn, which is subspaces of linear subspace. And we're going to say that Ru is the set of pairs x, y. Remember, these are pairs of tuples, such that if I take x minus y, this is an L tuple. I compute the span of that. This is exactly equal to U. Okay, so this is what the scheme is going to be, right? And again, we claim that this is symmetric. Shurian, well, translation, I guess. So I'm not going to prove self-dual, but after all I say today, you actually can derive that it's actually self-dual. But anyways, so let us notice now I'm not actually doing over binary, but I still get symmetric for a very silly reason. You know, span doesn't care about minus, right? So that's why it's symmetric. Translation is obvious because if it's a scheme, translation will be obvious because it only depends on x minus y. So I'm going to show that it's Shurian. And the way that we're going to show that it's Shurian is essentially using some of the actions that we already saw. But as the previous question by Yuval suggested, there's another natural action here. Well, one of them is SL, but actually I'm going to use an even better action, which is the action of the general linear group. And the action here is matrix multiplication.
Vector in the top.
What?
On the each vector in the top.
Yeah, so no, it's matrix multiplication between two matrices, and I will tell you why. It's because we want to think of X as a matrix. So if I give you some.
Acting on each one.
Yes. Yes. So if you want to skip that, you can just say, well, if I want AX and I want to know the JF code word, what I want to do is I take the sum over T in L of A J P X T. And this is a vector. It's not a point. This is a vector. But another way you can see it is you can say, well, the X corresponds to a matrix, which looks like you put, X1 here, XL here, and A dot X is going to correspond to the matrix AX. Okay, so that is the action.
And A is an invertible matrix.
Yeah, A is an invertible matrix, right? So now it's obvious that in this action, not the diagonal one, but in this action, two tuples are in the same orbit if and only if they span the same space. And then when you put this action together with our favorite action by translation, you get again this weird semi-direct product. This theta FL or in F. And our scheme is exactly the Shurian scheme of this action. Okay. So this is the other scheme that we are going to use. Now we need to argue that we can actually use this scheme because we're interested in the original Hamming scheme or in the original order L Hamming scheme. I guess it's under this board. And we need to argue that I can actually work over this, right? And I'm particularly interested in these DL lins, right? Now, the point is that, well, if I'm given some DL lin, I can also define this D hat L over this scheme now, which is like this, is just the RUs such that for every X in U, the Hamming weight of X is in D. Right, so I can just define this, and it's very easy to see that if you look at the graphs, if you look at the graph corresponding to the HN LF corresponding to that DL lin, this is exactly the same graph as if you look at this scheme corresponding to this D hat. Right? Is everyone clear about this? Right, you take two code words and you're going to check, well, in one case, you want that their configuration are such that their image is contained in D. Well, what is their image? Yeah, you take anything that is in their span and it needs to have Hamming weight in D. And here is exactly this, right? Because you take some space and you take anything in the space and it's in D, right? So these two graphs are the same. Maybe I call this G. So why is it that I can use this scheme to study that guy? Because, well, if you take by Schreiber's result, we know that the optimum of this guy is equal to the theta prime of this graph, but the graph is the same on the other side, and then you can use Schreiber's result to say, well, it's the same as doing the Delsarte LP. Okay, so all I need to show is that the other scheme is complete, right? That the other scheme actually
there is no direct. You have to use Schreiber's result.
You have to use it. It's the same program, so this is a very easy.
Yeah, I know. Yeah, but yeah, I wonder if you have to pass through this. Doesn't matter. I just wonder. Yeah.
No, I think maybe there's a way of avoiding, but this is a very easy way of doing this. Because you're essentially, you have the whole space, and in one of them you factor one action, the other you factor the other action, right? So that's what's going on. There's also a scheme where you factor both actions, but for the completeness, it's annoying if you also factor the Hamming scheme one. It becomes annoying to work with that. Okay, so now we're going to work with this other scheme where what matters are the subspaces. And I think I have the Delsarte LP written in one of the sideboards. I think it's written in general, but I also have the version for this scheme. Right under here, so just make it easier. So I just changed a little bit the notation. Instead of doing A sub R, I'm doing just A of U. And here the L is that L is this set of subspaces, right? So it's the same program. And I also am cheating a bit and I already wrote the Q function as some weird Krochuk of subspaces, right? So this is flipped. It's K V of U. So there's some Krochuk that is corresponding to the PQ functions. We're actually going to see how to compute this Krochuk. It's not that hard for the subspace scheme. this we're going to see it explicitly. But this scheme is much more convenient to work with.
The relations are just all subspaces which are default.
Yes, yes. The relations is all subspaces that are defaults, exactly. But I'm going to work, now I'm going to even forget about that, and I'm just going to say D is just a collection of valid subspaces. I don't even care that they're coming from distance, right? Because now I'm going to prove the completeness in general. So let me perhaps even state this. So what we're going to show is that if D is contained in L, I guess you need is downward closed. This will need, I don't remember where I use this, but I do use this. Then, well, and L is greater or equal than N, then every optimal solution of this LSNLF program of D is integral. That's what we're going to show. So what do I mean by integral? By integral, what I mean is that is a convex combination of true feasible solutions. Yeah, I will say that. So feasible solutions is obvious. What feasible means. I will say what is true solutions. True solutions is anything that actually comes from the code, come from an actual code. So what are these solutions? Let's just review. So true solutions. So if I have some code C in L, the true solution is of AC, right? So what do I do here? Well, remember, this is the configuration, but now I'm over the subspace scheme. So all that I have to do is I need to sum over all code words in my code, which is C to the L, that span U, right? Okay. And this is very easy to do. Oh, sorry, span of X is equal to. And this is very easy to see what it is because
X is span of the configuration or span of the elements in the spectrum.
Yes, it's a vector L tuple of vectors, and you look at its span, and it needs to be exactly U, right? So what do you get? Well, there are two possibilities. Either C is contained in either U is contained in C or it's not contained in C, right? If U it's not contained in C, then of course you cannot get this, right? If U is not contained in C, you cannot get this because you're taking code words here, but you want them to span U, but U is way larger, so you cannot span it because there are code words in U that are not in C. So you need U to be contained in C, otherwise you don't stand any chance. And once U is contained in C, well, then it's easy because you're just going to say how many code words do span U, right? And then we have something for this. This is exactly the valency, right, of the scheme. That's the definition is how many code words have the span exactly U, right? How many tuples of code words have the span exactly U. So this is the formula for the true solution, right? It's this thing here. So what this theorem is saying is that if you give me any downward closed D, and you look at optimal solutions of these guys, then they're always convex combinations of these guys, okay? And in particular, this gives you completeness, right? Because, well, they're going to be true combination of true feasible solutions. None of them can be of lower value because this was optimal, right? So then you get that this is a combination of true optimal solutions, right?
What is downward closing?
Oh, downward close means once you have a set in L, you also have its subsets, its subspaces.
It's subspaces. Okay,
Yes,
so it's,
yes. It's the usual notion. And in fact, this is a hint of how we're going to handle this. We're going to remember that this set is a closed set, right? So there's a natural order here, which is inclusion under subspaces. And if you know your inclusion exclusion and you think poset, you should immediately think Mobius inversion. And that's what we're going to explore here. So just before I get to the poset structure of this, the idea of going to this is, well, if we're hoping to show that this is a convex combination of true solutions, it better be the case. Well, it doesn't need to be the case, but it would be nice if these true solutions actually span the space, right? You take the space of all functions over subspaces, right? Functions that go from subspaces to, say, complex numbers. It would be nice if these guys span the whole space of functions, right? It doesn't need to be the case for steering to hold, but it would be nice. And it's very easy to see that it is by just looking at something like, well, the poset structure. You can just see that each guy includes the, this function is the only function that has C in its support. If you just look it downwards, and then by a simple induction, you can see that it spans, but we actually want to know how does it span. We want to say, given an arbitrary function, how do you write it as a linear combination of these guys? Maybe the combination is not of positive coefficients, maybe it doesn't add up to 1, but let's see, how do you write this? So let me remind you of the poset structure here. So again, we're working with this L, which is the set of linear subspaces of Fn, and it's a natural poset with inclusion, right? And it's more than just a poset. It's actually a Boolean algebra. The bottom guy is the zero space, and the top guy is the full space. And if you're going to do Mobius inversion, might as well define the set of intervals. So it's just the UVs, such that U is contained in V, and you have a natural convolution based off of this. So this convolution is not Fourier transform convolution. It's just convolution of posets, where convolution of two functions over intervals is you sum over all the W's in between, FUW, GWV, okay? Now, the nice thing is that this convolution behaves as a multiplication. So this is a ring with point-to-point addition. And if it's a ring, you can ask about the inverses. And there's a particular function that is very useful to us, which is the constant one function. By constant one function means constant one on the intervals. This is the zeta function. You can show that this is invertible, and the inversion of that is called the Mobius mu function, or Mobius function, which we denote by mu. I guess I didn't write what mu is in this case. It's not important for us. It's only important that it is the inverse of zeta, but I will write mu here. So mu uv is just -1 to the dimension of v by u, size of f, dimension of v by u, which is 2. This is not easy to prove at all, and it's not important for us. It's just important that it's the inverse of zeta for us. Okay. Now
it's not. I mean, or maybe it's not true.
It's not true. Yeah, you have to do some tricks, but it's not, just by staring at the definition. It's not, doesn't come like, it's not one line. You have to do some argument. Now, it will also be convenient to have some standard ways of turning functions from L to C into functions from intervals to C. And there's 3 ways that I will care about this. Also, I should also say a function from I to C, you can think of this as matrices, as very particular matrices, because UV is in L cross L, but they're kind of like just upper triangular matrices, right? Because if you order the elements of L in something that is compatible with the poset order, then you can see that functions like this is just, they need to be upper triangular. Not every upper triangular comes from a function like this, because the support needs to be on comparable points, but they need to be upper triangular, and that's sort of
order them by side, by dimension.
Yes, for example, if you order them by dimension, you get that the matrices corresponding are upper triangular. Not all upper triangular come from this, but all of them are upper triangular. And so it will be convenient to, when I have a function just over L, to define a corresponding matrix of that, or a corresponding function from I, and it's HL, HD, and HR, and these names are suggesting L for left, D for diagonal, R for right. L for left means I only care about the left guy, so it's going to be H of U, but I care that the other guy is 1. Diagonal means diagonal. It's H of U, but you care that both of them are equal. And HR is you compute in V and you want the other one to be 0. So in matrix form, HL.
This was too fast. The first one, HL is a matrix, right?
Yes, all of them are matrices.
Yeah, but H itself, you apply H to U. H is the
Some function. But on the base space, on L.
Yeah, so H of U. So what do you see a matrix?
Oh, it's a matrix because this is of UV. And you want V to be 1 and you apply to the rest.
Okay, got it. Yeah.
But here's the picture. So HL is you put H on the first row. HD is you put H on the diagonal. And HR you put H on the rightmost column. That's what these things are doing. Okay. It's just that it's convenient because then I will, instead of thinking of multiplication by a vector, I will just keep doing matrix multiplication everywhere. The other thing is that because this is a diagonal matrix, it's very easy to know, well, when this is invertible is exactly when H doesn't attain 0 values. And when it doesn't, it's obvious that its inverse is 1 over HD, right? It's just invert all the values of H and still put them in the diagonal. Okay, so this is just notation. Right, so the point is that we want to describe this, we want to describe an arbitrary function as linear combinations of these guys. So what we're going to do is we're going to do a small definition, and maybe let me just get the formula because I don't want to get it wrong. So we're going to say, if I give you some function from L to C, I'm going to define PA. So it's another function from L to C, and it's going to be defined like this. You sum over all V's containing U. Wait. U, U, V. Remember, V is the valency, so we're just going to do this definition. Another way that you can see this is using that weird thing that I wrote there. It's written like this. It's just mu star 1 over V star AL. That's another way that you can see this. Okay. This is just a definition for by this point.
AL and A are the same thing.
Yes, A is this function, right? So
But you want AL in the
L stands for this L nonsense. So you can think that it's a vector if you want, right? It's a multiplication of this matrix by this vector. But if you have this, these guys are invertible, right? Remember, valency is never 0. So this makes perfect sense. And these guys are invertible, so I can use this expression to write AL as the opposite. So I need to invert this and then invert this. So I'm going to get VD star zeta star L. Right? Okay, this is just passing to the other side. And now let's open up this definition. What I'm going to get is that this is AU is equal to, well, VU sum over V containing U of zeta is 1, so you're going to get P of, that's what you get. Okay, it's just opening up the definition. And then let's just rewrite this in a slightly different manner by writing this like this.
This PA.
PA, yes. PA is this P that's defined like this. And then you can write this in a slightly different manner by saying this is in DL. Maybe I'll put VU inside. So I just rewrote, so I put the condition into an indicator and I put the VU inside. But the point is that, what is this? This is exactly the true solution. This is the true solution corresponding to the space V. evaluated at U, of course. So what I showed here is that A can be written exactly as this linear combination of V's in L's, P, A, B times A, B. So these PAs are exactly the coefficients that change you to the true solution, right? That's what this computation is saying. It's just a Mobius inversion, essentially, that we're doing.
Yeah, but summarize it again. So we have these functions. For every code, we have a function. We want to show it's the basis for all functions.
Yes, but I need the explicit description of this basis.
Yeah, I'm just checking what you did. I understand you will need it. So what you did, but what did you do? You took now an arbitrary function.
Yes.
Of this family of subspaces, and you showed us that you showed us an explicit way of writing it as a linear combination of these two solutions.
Yes. Yeah. Yes. If you just wanted to see that these are spanning, is much easier because you can just say
somehow you call it AB. Okay, so V and C are.
V and C is just.
But it's not necessarily, because C was already maybe a code.
Here V is a subspace, which is also a code, right?
Yeah, but it doesn't have to be a decode.
No, it doesn't have to be a decode. So here I do want to hammer this home. When I say true solution, I don't mean true feasible solution. These are different things. True solution just means corresponds to a code, doesn't need to be a decode.
Oh, I see. So that doesn't. Okay, so you get integrality.
No, but here in the result, I say true feasible.
Yeah, of course.
Yes.
You have these conditions are anyway in your linear program.
Yes, and then if it was true, but you included something that's not feasible, you're going to see very easily that some restriction is not satisfied. Yes. But it's useful to think that all of the codes could be involved a priori. Okay. Any more questions? Okay, so the idea is that now we're going to change this program into this weird P basis, right? So we want to think that instead of working with A's, we're going to work with P's, right? There's a very natural correspondence that is being given by these two formulas, or if you want, here and here, right? Now, before I do that, I will need to, this is just a preparation, which is related to the project. So the point of this.
Before so what's the plan? I mean, in high level. So
the plan.
You have this, and you want to show that this program captures the side of the code.
Yeah. So the idea is that we're going to rewrite this code using the P functions rather than the A functions.
And then what will be used?
What is the magic? The magic is that the crotchets will become much simpler. When you change to the P basis, the crotchet functions will become much simpler. The crotchets that appear over there. And so we'll write this as a linear combination of the using the P's, right? So there is a formula.
So it will somehow transpire that this are already written as a convex combination. So.
Well, not that easy, but the program will become much nicer. Because the problem of the program here is that these guys are alternating functions. So what we're going to do is we're going to rewrite this on this P basis, and what is going to happen is that nothing will be alternating. Everything will be positive. The problem is that P might be alternating, right? P might have negative values, right? And then we need to argue, but optimal ones cannot have that. That's the plan, okay? So just a preparation, which is based off of the crotchets. So it will be convenient to sort of transpose the crotchets. So I will write this different notation, small k LV, to the transposed version of the crotchet. So this was the usual crotchet, but we would do, sorry, maybe I will write it like this, UV. This used to be like this. So I'm just swapping. I want V to be the parameter, not the index. And this is just a reminder, because this was a translation scheme. You could write this as just saying you sum over all y's such that the span of y is equal to v, the character y at x, and x needs to be anything that has span exactly equal to u. For anything that you pick that has span equal to u, that is the formula for the crotchet. So I'm going to do sort of the transposed version of this because So the problem is that this is not that easy to compute, but there is a nice one that there is something similar that is easy to compute. And spoilers, it will be related to the project that actually appears when you get, when you change the basis, which is, let's simplify that condition and just say that let's just sum over all y's in V to the L. They don't need to actually span V, they just need to be in V, character yx, and so I'm still assuming that the span of x is equal to u. And of course, if I do this, it's obvious that this crotchet can be written in terms of the previous crotchet, because you can always say, well, you just take any w's contained in V and you sum the previous crotchet, right? K, L, U, W, okay? Just from the basic formula. But the point is that this is much, much easier to compute, because what is this? Well, this is just, f to the n to the L times the Fourier transform of the code V to the L evaluated at x, right? Which is very easy to compute, right? Because this is just the Fourier transform. This is indicator of the dual code, the L perp, evaluated at x still, times the size of the code, which is V to the L. Well, V, sorry. I guess it's V. Yeah, okay, sure. V to the L. Oh, okay. Yeah, my notes are flipped. That's what's my note. By F to the N to the L. And so this cancels. So you get V to the L. And now let's look at this. Well, X is something that has span exactly equal to U, right? And of course, V to the L perp, this is equal to the V perp L. Commute these two things. And now if X is equal to, has a span equal to U, then the only way that this is going to survive is if U is contained in V perp, right? Okay. So this is the formula for this tilde. And I also need to massage this a little bit. I guess I'll go here. So from this formula here, K tilde L U V is equal to the sum of W contained in V, K L U W. This can be rewritten using that weird thing that I wrote there, as you take KR and you take zeta star KLV R, which means that you can pass to the other side with the mu, right? So KR LV is equal to mu star. So if you wanted to know what was the project, you can just follow this formula. Right? If you wanted to know what was the project, this form, follow this, right? Of the original one. But now we'll mostly be working with K tilde. Because the point is that we want to show this let's consider the L hat, and now I'm going to start being a little bit brief and not writing NL, etc. Let's consider this linear program where I do sum over U and L, K tilde, LU, L0, sorry, LU, PU, such that sum of U and V, tilde LV, U, PU, is 0, v, sum of u and L, u is 1. Let's consider this linear program, and what we're going to show is that.
So let's go over the linear program. I mean, the optimization just comes from the description of what the A of U's are. And this is an empty set, right? On the subscript.
Yes, 0 is not the empty set, the zero space.
The zero space.
Yes, yes. And yeah, so the point is that what I'm going to show is that this is equivalent to this.
Yeah, but,
Right, when you change the function. Okay, so yeah, what I'm going to show is that A.
But basically, you did the linear transformation from the A's to the P's.
Yes. L, if and only if, or LD, if and only if PA is a solution. Now at D, the same value. That match. That's what we want to show. Okay. So let's see that, and then of course we will use. Oh, I should not have this. We'll show this, and then of course then you plug in that formula here, and you can massage this. But anyways, let me show this. So let's start with this guy. You take the sum. L, U, P, U. So let's think PAU. B. So one way you can write this is you can say, you can write it like this. This is.
You took V as solution, right? I mean,
Oh, sorry, this is not U continuity. Yeah, no, this is not U continuity. This is yeah, this is U now. Okay. Yeah, okay, that's much better, because now this is no. So I'm just saying, take any function and consider its corresponding PA, and we're going to see that this is just translating one of the. Well, it's translating the Maclaurin's inequalities. It's just the Maclaurin's inequalities in this guy, because this guy you can just write it. Sorry, it's K tilde. K tilde. This guy can write like this. It's this convolution here, evaluated at 0, 1. But now we can just plug in what we know. Well, K tilde. Wait, I did zeta from the wrong side, I think. Yeah, I did zeta from the wrong side. Sorry. It's like this. Because the point is that you're going to get something nice here. V star zeta star. Now what is P? PL is written right there. Mu star 1 over V. Now, 0, 1. Now this cancels because they're inverse of each other. So what you're going to get is this KR LV star 1 over VV L 0, 1. Then you open this up, you get something like this. K. Let me also use the actual project. So the actual project actually flips the thing. So, okay, maybe I'll do it more slowly. So you get this. Now you have to remember that I flipped my project. So this is now project L U V over V U U And now you have to remember that there's a formula to unflip the Krochuk, which gives you 1 over VV. So this is morally the Macmillan's inequalities that appear here, except that I have this multiplicative factor, but this is a non-negative multiplicative factor. And in fact, if you look at the objective value, this also matches the objective value, because you have to remember that when V is the 0 set, this function is the constant one function and the valency is 1. So this gives you both that these things are the translation of this and this. Okay. Now, perhaps I'll skip the other one because I'm sort of running out of time.
That's just applying the linear transformation.
Yeah, so you apply the linear transformation and you get the other ones.
Yes, you need, yeah, but they may be negative.
They may be negative, yes. Now, and then you also apply this computation that we did for the Krochuk tilde, and what you get is the program that is over here. So it now looks like this. So it all depends on just these powers of u to the L, and the fact that it's contained in V perp, you can change the variables, and it's u contained in V, right? So now we need to show that this guy is actually going to be integral. So let's show that. So the first observation is that you can do an easier case. So I'm going to do the easy case first, but the hard case is just easy case plus a very simple step. So easy case, let's consider the case that I have dk is the set of all spaces such that the dimension of u is at most k. Right? It's a silly program to try to solve, because you already know what's going to be the optimal solution, but let's just consider this one. Almost nothing that comes from distances will actually look like this, but this is an easy case. And what we want to show is that, so I want to show that if P is optimal, then the support of P is contained in U's such that the dimension is exactly K. And E is greater than. So why is, well, okay, so let's first see that why this implies this. So if I could show that the support of P is completely contained in the top guy, just from these kinds of restrictions, you can see that P can only be non-negative, right? Sorry, this restriction, right? Because you only have a P can only live on the top layer, right? And this is saying, well, if you sum everything above you, it needs to be non-negative, right? So this shows that P is non-negative, right? And also, once I know that P is non-negative, this restriction is saying it's a convex combination, right? So these two things together. So first, this guy is going to imply this, and second, this implies that the corresponding P, the corresponding A, is integral.
I didn't get the logic. You start the DK, these are the, you allow only subspaces which are.
Yeah, so I'm solving a different.
What the answer is, this answer is
Yeah.
K or 2 to the K or whatever,
Yeah.
the size of the code.
I'm not dealing with the general case.
You put a stronger condition on the convex combination.
Yeah, no, I'm going to show that if you give me any optimal solution, then the support is contained in the dimension K. For this particular problem, not the general one, right? And once I show this, it's obvious that P is non-negative, right? From this restriction, because it's a feasible solution. This restriction shows it's non-negative, and this restriction says sums to 1. So there is a convex combination. So this means that the corresponding program that lives before the change of basis, A is an integral solution, even though I'm using something that is not really what I'm interested in, right? Okay, so let's prove this. This is sort of the main point. Okay, so what we're going to do is we're going to say, so let's look at this this linear program, right? And let's forget for a second that P can have negative values. If you look at the objective is sort of saying you want to put more mass on larger spaces, right? So the idea to show that this is true is we're going to take some optimal solution and we're going to say, if it's not supported on the top space, we can push some mass up, right? That's what we're going to do.
Assuming no negativity.
I'm not assuming non-negativity. So I need to claim that the mass that I'm going to push is actually non-negative. So I will need to prove that, but yes. So what we're going to do is, let's say U0 in the support of P of minimum dimension. Take this guy of minimum dimension, and let's say that the dimension is K0, right? And let's suppose towards a contradiction that this is less than K, right? Okay, so now what I'm going to do is I'm going to define a set C, which is all the guys that contain U0, and the dimension is exactly one above. Dimension of U, 0 plus 1. And of course, this is contained in dk, right? And we will also need a trivial upper bound on the size of the set. And it's very easy to see that this is certainly at most f to the n, because you start with U0, you can add at most one vector, cannot be the 0 vector. There's a trivial upper bound. And now we're going to do this thing of pushing the mass up. So let's define a new solution where we're going to say, well, it's going to be 0 if U is U0. It's going to be PU plus a little bit of mass. If U is in C, and it's going to remain the same otherwise. So what I'm doing here is, here's U0, and here's C, it's the guys that are immediately above, and I'm pushing mass equally upwards through this guy. Now I need to check that the mass, if for sanity check, I said, you want mass to go up. But you just know that this guy has non-zero mass. It could have negative mass. Well, it cannot, right? Because, so if you look at, say, this restriction, when V is equal to U0, you're going to get something like sum of U containing U0, for U below U0, of U to the L, P to PU. But this is just U0 to the L, PU0. Therefore, PU0 it's greater or equal to 0, but I know it's not 0. Okay, so I'm actually pushing mass up. So all I need to do is to check that I'm actually retaining feasibility and that I'm improving the objective value, right? Okay, so let's do that. Let's look at these three on the bottom first. So what is sum of P star U, U in L, or U in, so let's say U contains V. So there's a P star is this new solution.
Okay, yeah.
So we need to see how much it changes. So let's see. So maybe let me just consume too much time. The case that I want to split in. Okay, so let's consider the first case where V is not contained in C for every C in calligraphic C. Well, if V is not contained in any guy in C, when I take guys above it, I only see things that did not change, right? Because the only things that change is U0 or C, right? And everything that is not below any guy in C, is the things above it will not change. So this is just the same thing, right? Which is greater or equal than 0. Okay, so then let's consider the case where V is equal to U0. I guess it's the next one. No, it's not. if you take V and C, then it's easy because what you get is whatever you had before, but you got some additional mass, right? Because I pushed some mass up. Right? This guys is all the things that are above or equal to V. And if V is in C, it just got some addition of a mass, right? And this is non-negative, right? This is still fine. So now we just need to see what is the case that is missing, which is probably something like V is contained in 0. This is the case that is missing. And now it's easy because once V is contained in U0, it's the same sum, right? Because now everything cancels out, right? Because you get, you get minus PU0 because you lost the mass on U0, but you see all C and each of them gain PU0 C. So then it's fine, right? So this is greater or equal than 0. And moreover, if you take V to be the 0 space, it didn't change. So even the equals 1 is still preserved, right? So this handles all these 3 guys. You have to check that sheet, but okay. So let's just check the other one. The other one is the sum. Okay, so now let me see the cases again. Okay. So the first case is V doesn't contain U0. So if V doesn't contain, oh, sorry, this is U contained. And then it doesn't change, right? Because if V doesn't contain U0, it doesn't change. This is a trivial case. Then you have the case where V is equal to U0. Well, in the case V equals to U0, you get.
The summation should be for all U and L, no? This is the objective part.
No, both the objective and this. I'm checking both of them.
Okay, yeah.
So this didn't change, so this is greater or equal to 0. The objective will come from the third case as well. I have to check is greater or equal than 0, but it will also come from the third case. So in the case V equals to 0 is slightly more technical. You have to remember that U0 is picked as minimum, right? So everything below U0 is already 0. And in P star, U0 is also 0. So this case is 0, right? Which is greater or equal than 0. So I'm fine. So the only case that I'm missing is when V properly contains U0, right? In particular, it covers the objective value, right? And in this guy, well, what I'm going to show, this was equal, this I'm only going to give a lower bound. So I'm going to say, well, you had this, right? But now because I properly contain U0, well, I lose U0 to the L, PU0, right? But because I properly contain U0, I need to contain at least one guy of C. So that gives me at least, size of U0 to the L, F to the L, because that is the dimension of anyone in C. And I have at least one of these, right? And now this is nice because when you put things in evidence, you're going to see something like U0 to the L, PU0, this is now negative, and then you're going to get size of F to the L over C minus 1. And this is greater or equal than 0 because C is at most F to the N, is strictly less than F to the N, and L is larger than N, larger or equal to N, right? So this is actually even strictly greater than 0. So this both gives you the final restriction, and it also gives you that the objective is strictly improved because this is strictly greater than 0.
F to the L.
F to the L here.
C is.
C is the size of the family, which is at most F to the N.
It's most F to the N.
Yes, but L is at least N.
Oh, yeah, of course.
L is at least N. So then this is at least F to the L over N, right? Which is fine. And C is strictly less than F to the N. That's why it's strictly improved. So this shows the easy case, right? So now actually I'm done. Why is it that the hard case comes from the easy case?
one of these has some dimensions, so they will be,
Yeah, essentially is that. You're just gonna say,
which will be the K, it will be the optimal K.
yeah, you're just gonna say something like, for an arbitrary D, you need downward close because I don't remember what goes wrong, but you do need downward close. You set K to be the maximum dimension. And then what you're going to see is that L hat of D is L hat of dk plus extra constraints. Right, so this means that you just take a feasible solution of this, it's going to be a feasible solution of this. If it's optimal here, it needs to be optimal here once you check the values. But the convex combination is independent on where you are. And then here is, well, the combination is independent of where you are. And here it shows it's a convex combination. Therefore, you get it here as well. And that concludes the proof that this is the whole trick. You change the basis and now suddenly you can push mass up and it works. Yeah, so that is the
All right.